All right, hello and welcome back, everybody. This is day one or day two. Day one since the intro. Day two total. And what we're going to be doing today is looking over the NCEES website, which is the accrediting body for the fundamentals of engineering exams. We're just kind of going to look at the basics of the exam and you know how all it's going to work and. So basically what we have is the first step to licensure. The first pair of steps to licensure is you're going to need a engineering or bachelor's of science from an ABET accredited program. And then in order to become an engineer in training, you'll need to pass the fundamentals of engineering exam. The exam's going to be allotted for 6 hours. It's going to include 110 questions with about a 5 hour and 20 minutes of actual time to take the exam. Let's see what we got here. This is log on information. The exam fee, $175. Hopefully you can find a way to work with it. What else we got here? Reasonable accommodations. Exam prep material. So there is a reference handbook that you can use. Oh, okay. This is the only reference material that can be used during the exam. You'll be provided with an electronic reference handbook during the exam for access prior to your exam. You may either purchase a hard copy or download the electronic copy. The NCEES offers practice exams that contain questions that have been used on past exams and written for study materials to give you extra practice. They come in paperback copies. Online practice exams are no longer available. Okay. Interesting. Scoring and reporting. So 7 to 10 days after you take the exam, you'll receive an email notification from NCEES with instructions on how to review your results. You probably have to log into some site and, match up a verification code or whatever to make sure your results are your results and not somebody else's results accidentally. Let's look at the pass rates. So it looks like an overall trend of 65 to 75% pass rate, with the industrial and systems being the lowest, but it also has the lowest volume of students taken, whereas the civil exam 69% pass rate, but it's got the highest amount of students taken within this relative sample size of first-time exam takers had a degree from an accredited program and took the exam within 12 months of graduation. So results are promising. It's over half, which isn't bad. The highest pass rate the highest overall pass rate is environmental. The highest per capita pass rate would be mechanical. So it's interesting. I wonder why that is. And then below that we've got if you took other disciplines that were not the main FE disciplines that are issued. This is much either the general engineering, naval architecture, and marine. Interesting. That's a really high pass rate, but it's a select few, I'm sure, that's well trained in that field, and it is probably set up to prepare for that exam exclusively. The general engineering, very small amount taken, but very, very high pass rate for that amount. Interesting. Outcomes assessment and the about page. All right, so let's move on to the civil exam specifications. Good, we can see that. Let's pump it up, pump it, pump it, pump it, pump it, pump it. And maybe a little more. There we go. We want it to be, well, one too big. There we go. Yeah, all right. Let's see, the fundamentals of engineering civil exam effective July 2020. This will be completely computer-based tests. You will use both customary and metric units. Let's look at the breakdown of the problems. So for mathematics, we have analytic geometry, single variable calculus, vector operations, and statistics with examples of distributions, mean mode, standard deviation, confidence interval, regression, and curve fitting. Okay, so this is pretty, if you made it through calculus 1, this should fit. This is a 8 to 12 questions, so this is going to be weighted pretty heavily, or will be more heavily represented subject. Next, ethics and professional practice, a code of ethics, professional liability, licensure, contracts, and contract law, 4 to 6 questions. So just some understanding of how the licensure applies legally, and what are the consequences of possibly having some unethical behavior, or any, I guess, sort of malpractice, but not a super heavy component of the exam. Next is engineering economics, where we're going to look at the time value of money, focusing on equivalence, present worth, equivalent annual worth, future worth, and rate of return. Then there's cost, fixed costs, variable costs, direct and indirect labor, incremental costs, average costs, and sunk costs. So those are two things that can be covered in any kind of business or economics or economic analysis class, possibly even in some statistics, but mostly your economics class. Then we got analyses of break-even, benefit, cost, life cycle, sustainability, and renewable energy. So I guess just kind of looking at over time costs of things, and then uncertainty, and being able to calculate expected value and risk. This is 5 to 8 questions, so more middle presence expected to show up, but no guarantee. It won't be as heavily weighted as some of the other sections. There we've got the big statistics. Excuse me. This is going to be resultants of force systems, equivalent force systems, equilibrium of rigid. Oh, statics. I was about to say, this is very physics-driven statistics. No, it is statics, and I cannot read. Yes, resultant of force systems, equivalent force systems, equilibrium of rigid bodies, frames, and trusses, centroid of area moments of inertia, and static frictions. This is the physics of things that don't move. It's going to be a lot of summation of forces, equations, and if something's this long and has this much of force applied to it, and the fulcrum is here, How much is it going to deflect or bend, or what's the resulting force, something like that. But you set the sum of the forces to 0 because it is static and not moving. 8 to 12 questions. Going to be a pretty heavily represented on this exam. Next, we've got dynamics, which is kind of the older brother of statics. So kinematics and particles, rigid bodies, mass, moments of inertia, force, acceleration, work, energy, and power. So this is now you're taking the concepts of statics, and now the object is moving, and now you have to solve for things like moments. There will be, you'll be given if it has this mass and travels a distance over time. We're going to find out work, energy, power, outputs, how the when the total forces don't equal to 0, how is it going to affect the object? 46 questions, pretty lightly represented. Statics and dynamics are going to go pretty hand in hand. They build off of each other well. So, if you can show up strong in statics, you're going to have a good shot at performing well in the dynamics area. It's just going to have a little bit of a little bit different variables and a little bit different scenarios than you might be used to if you just did statics by itself. Next, we have mechanics of materials, shear and moment diagrams, stress strain curves, deformation, combined stresses, principal stresses, and Moore's circle. Very cool. All right. Yeah, a lot of torsion, bending, shear stress, axial loads, thermal. That's something I have not done before. How is heat going to affect the performance of the material? That's something that I definitely did not have a whole lot of formal education on. Will be pretty new for me. But stress strain curves, very standard for any engineering discipline. I spend a lot of time on, is it gonna fail type of problems. Here's your loads and your scenario, and then here's the type of the material, and then you look at the stress strain curve and say, all right, how many megapascals is this going to take before it breaks? And I don't know how far it'll go as to like, oh, would you recommend a different type of material or something like that? And then we have materials, mixed design of concrete and asphalt, test methods and specifications of metals, concrete aggregates, asphalt, wood, physical and mechanical properties of metals, concretes, aggregates, asphalt, and wood. Okay, so I guess this is more of the chemistry side, and it'll tie into mechanics of materials a little more on like why do you get these certain stress strain curves. Oh, also back to mechanics of materials, shear and moment diagrams. Also statics and dynamics are going to be your moment building block. So it'll be a lot of information pulled from here will certainly be applicable here when you're trying to calculate shear forces and how much total force is going to be applied on the object, and then you take your stress strain curve and say, okay, is it going to fail or not? 7 to 11 questions, by the way, very very strongly represented. You're definitely gonna a lot of these are going to be intertwined. You're going to see mechanics, materials, statics, dynamics. And they're just it's going to look like one big bundle that'll build off each other. As far as materials go for concrete and asphalt, this is something I very not studied as far as like construction materials go. That's my degree was in manufacturing engineering, and so I'm a little uncertain of how well this would apply. But like in as far as I did not have courses that were specific to concrete and asphalt and how they react. Properties of metals, very familiar with, but wood, no, I have no, I have no understanding of the properties of wood. That would be a new one. But materials is not a very large section. Only 5 to 8 questions, so this will not be super heavily represented. Let's check and see how we're doing real quick. All right, it looks like everything's going well. Let's keep going. Fluid mechanics, flow measurement, fluid properties, fluid statics, energy, impulse, and momentum of fluids. 6 to 9 questions. This is another section I have no experience in, and we'll definitely need to spend a lot of time preparing for. What else have we got? Surveying, angles, distances, trig, area computations, earthwork, volume, coordinate systems, state plane, lat, long, leveling, differential, elevations, percent grades. This 6 to 9 questions, so not super heavy, but it's going to be there. This is actually very relevant to my work experience, and I spend a lot of time in the surveying world, and so definitely gonna try and pull on that as much as I can to see how much of it would be relevant here. Then we have water resources and environmental engineering, basic hydrology, basic hydraulics, pumps, water distribution, flood control, stormwater collection systems, groundwater, water quality, testing standards, water, wastewater, 10 to 50. Wow, so very, very heavily represented. And this is a subject I know nothing about at all. So that's going to be a big study point. Then we've got structural engineering, analysis of statically determined beam. Oh, statically determinate beam. Okay, so beams, columns, trusses, frames that aren't moving. Deflection of statically determinate beams, column analysis, structural determinacy, elementary, statically indeterminate structures. Okay, so if you can't figure out if it's static or not, I'm really not sure. Loads, load combinations, load paths, design of steel components, design of reinforced concrete components. Oh my goodness. Geotechnical engineering, index properties and soil classifications, phase relations, lab and field tests, effective stress, stability of retaining structures, shear strength, bearing capacity, foundation types, slope stability, soil stabilization. This is another. Did not spend a lot of time in this aspect. We were very my engineering elective courses would have been very focused on factory design and process control and improvement, not super mechanical dependent. Or transportation engineering, geometric design, pavement systems, traffic capacity, flow theory, traffic control devices. This is all going to be movement. That was 10 to 15 questions on geotech, 9 to 14 on transports. This is going to be a big chunk. If you want to go water resources, structural, geotech, transportation, this is going to be a big run. You're going to see a whole lot of that available. And then finally at the bottom, construction engineering, project administration, construction operations, project controls, construction estimating, interpretation of engineering drawings. So that is what you need to know if you want to take the civil exam. And now that I'm looking at it, I'm like, holy cow, I wonder if I should probably move for one that's a little bit more relevant to me. let's take a look at, let's go back here. Let's take a look at other disciplines. Let's see. Okay. So we've got the same kind of mathematics, probability and statistics, chemistry, instrumentation controls, engineering, ethics. So controls, sensors, data acquisition, logic diagrams. This is something I had courses in. This is going to be more relevant to me. Chemistry, just kind of a general chemistry, oxidation, reduction, acids, bases, react. Can you do chemical equations? Any of that basic stuff. Probability, statistics, estimation, expected values, sample distributions, goodness of fit. More familiar with that. Health and safety, industrial hygiene, safety equipment, gas detection, electrical safety, confined space. These were kind of sprinkled into all of the different kinds of labs that I did. I didn't have like one course that was specifically tied to health and safety, but it was always kind of an element within my coursework. Engineering, economics, time value of money, very important in any economic calculations. Cost analysis, economic analysis, uncertainty, project selection. Yes, comparison of projects with unequal lives, very relevant to me. And, lease, buy, make, figuring out, if I've got this product that costs this much and it's going to have this expected lifespan, and this other product that costs less but also has a shorter expected lifespan, there's a series of calculations that you can do to figure out what is the most economically effective solution to go by. What else have we got? Statics, vector analysis, force system, blah, blah, blah. Free body diagrams. All statics always starts with free body. Statics, dynamics, mechanics, and what, I don't remember what that other part was. Anyway, any of those kinds of problems where you're solving for forces, always start off with free body diagram. Really helps you visualize, your problem and how to best approach it. Next is dynamics. So we've got we got particle, rigid body kinematics, linear motion, angular motion, momentum, dynamic friction. Because when things move, now friction matters. When things don't move, friction doesn't matter. But when things move, now friction matters. And it's all it is just another force that you tack onto the free body diagram, and there's a coefficient of friction that you solve for, and you basically just take your mass and how far you're moving and whatever the coefficient of friction of the material that you're on, and that'll give you how many newtons is pushing against whatever the direction of motion is. Because remember, friction is always going to be opposite of the motion that the object is headed in. Also, normal force. When you're drawing your free body diagrams, don't forget about normal force. There's one to keep you from flying away, and there's one to keep you from crashing through the crust. And that's normal force. Strength of materials, stress, strain, shear moment, analysis of beams, load deformations, material failure, creep, fatigue, brittle fracture, stress fractures. So failure is an interesting thing because it's not always like, okay, I've got this constant load on this one spot and it's going to be there all the time. When you look at like the bolts that hold your wheel in place on your car, that's going to be something that fails due to fatigue over time, because it's going through stress cycles depending on where what position it's in relative to the rest of the car. It's going to have a different kind of load on it, and as you drive, it's going to cycle through its load over and over and over, and that can increase the failure time depending on how many cycles you go through. Creep is a failure. Creep is the failure that's the opposite of the brittle fracture. So the brittle fracture, you've got your thing, and then you put an impact load on it, and all the newtons go onto the spot at one time, and if it's enough newtons on that one spot, it'll fail. But creep is, I'm going to have this constant load on this one spot over time, and over time the material strength is going to weaken, and it will creep its way into failure. And there's a way to measure that, which is interesting. And then safety factors, allowable stresses. So it's all solving this, your statics and dynamics, and taking your taking that analysis and looking at your stress strain curve and going, all right, is it gonna fail in an unexpected or catastrophic manner? All things are gonna fail over time. You want to err on the side of it'll never fail, but sometimes there's like acceptable failure rates depending on what your situation is. Materials, physical, chemical, thermal, electrical. This is just understanding the property of materials in general. Will probably mostly be metals. Fluid mechanics. This is a whole thing that I'm not familiar with. But I'm sure at the end of the day you still start with a free body diagram. It is mechanics. Basic electrical engineering, electric fundamentals, current voltage, AC/DCs, rock-on, measuring devices. Can you read a multimeter? Three-phase power, motor efficiency, power loads, Kirchhoff, ohms, imaginary components, complex power factors, RLC circuits. No Wheatstone bridges, or maybe they use those as a part of the way to set up the problem. Interesting. And then thermodynamics. I moved that whole thing. Go back. There we go. Thermodynamics and heat transfer. And again, another thing I'm not going to be familiar with. But more. Just if you know your material properties, how does heat affect your material properties? And then you go look at your stress strain curve. Oh my goodness. Yep. That's a lot more relevant to me if I attempted the general engineering exam. Mechanical is probably going to be the most applicable, but not to my degree. Probability statistics, ethics, professional practice, engineering economics, electricity, magnetism. This is all the same. Heat transfer's got its own thing here. For mechanical design analysis. So this is something unique. that you're not going to see on the other tests. GD&T, geometric dimensioning and tolerancing, is a whole list of symbology that goes with interpreting drawing. Interpreting engineering drawings. There's a standard set of symbols that you use to identify mechanical engineering drawings, or drawings of parts, as opposed to civil types of drawings. Springs, bearings, screws, transmissions, gears, joining methods, manufacturability, quality, and reliability. These are all kind of extra pieces that are going to be in the mechanical world as opposed to the civil world, and didn't seem heavily included in the engineering world. The engineering world, the general exam seemed to just kind of go to the material properties and stop, and general statics and dynamics with just beam stuff in general, but not but like there was, it didn't seem like there was anything more complicated than an I-beam with a load on it. But in this one, you're gonna take your statics and dynamics and you're gonna apply it to bearings or gears or springs, and they're gonna have a little bit different behavior methods, and you're gonna solve for your moments differently because they're different kinds of shapes, and the way that forces act on them is going to be a little different. These are going to be, springs especially are going to be very susceptible to cyclical loading, and the failure rates that are resulted with cyclical loading. Pressure vessels and piping, that's new to me, but it does make sense as something being able to understand. It's mechanical in general. Let's give a shout out to the environmental dudes just to see what we got here. Wow, I made that too big. There we go. We're still good. Math, statistics, ethics, economics. You're going to see a general trend of math, statistics, and ethics are all going to be there. Wow, I'm surprised at how much fluid mechanics and thermodynamics have gotten involved. Ethics and professional practice in economics was relevant to the general engineering version of the test. Fundamentals and principles, material science, population projections, reactors, environmental chemistry, stoichiometry, health hazards, risk assessments, fluids and therms, surface water resources, and hydrology. So definitely, if you're going the environmental route, you need to spend a lot more time in the biology world. Groundwater, soils, water, wastewater, air control, solids and hazardous waste, and then just general energy and environment. Definitely not as many things relevant to me. The other disciplines is actually looking pretty good, because I do not have a civil degree, man, and there's a lot of parts of that civil thing that are looking pretty difficult, and I'm not entirely sure how it would fare. Okay. Now I'm starting to understand this chart. a little better. So the overall other disciplines pass rate, 68%. And then the breakdown of the degrees that those people had, the general types of degrees that those people had that took the other disciplines exam was ag, architect, bio, general, mechanical, naval architecture, and petroleum. I gotcha. That's starting. That's making more sense now. So yeah, so that's kind of it's kind of the whole deal. FE and other disciplines. I wonder how this would translate to the PE. What if I capitalized it? Ooh. I don't know how to spell disciplines. Fail. Okay, homepage. Engineers. None of that. Go back. What do we have for licensure? It's just kind of interacting with licensed people, how the boards work. Go all the way back. Well, all right. That's I think that's good. I think that's a good start for today. We've definitely made some progress here and gotten a lot of information done. So we will check out and see you next time.